Okay, we'll continue with 6.4 then. Okay. These vectors are linearly independent. Are they orthogonal? Are these vectors orthogonal? Are the dot product between each other equal to 0? They are not. So we want to construct the W, the span of U, the 3. We want to construct orthogonal basis of W. Okay. This is what we want to do. And the procedure is the following. V1 is going to be equal to U1. W1 is the span of V1, which is the same as the span of U1. V2 is going to be equal to V2, subtract the projection of V2 onto W1. Okay? And then you end up with W2, which is the span of V1, V2, which is the same as the span of U1, U2. And then you do one more time after this step, similar ones, which is V3 will be equal to V3 minus the projection of this. Sorry, this one is this one is a U. I need to be slightly careful. Okay. Okay. This is correct now. So this one will be V3 will be the U3 minus the projection of U3 onto W2. Okay? And then you end up with W3, which is the span of V1, V2, V3, which is the same as this span. Okay? And this is my W. So after this, we are going to be able to, then we are done. Okay? I think this is correct. Everything is correct now. So what is U1? U1 is 0, this vector, 1, 1, 1, 1. Okay? So this V2, okay, will be U2, okay? U2 is 0, 1, 1, 1, minus this projection, okay? Minus that projection. That projection will be U2, okay, which is this guy. Dot U2 dot V1. over the square of this guy, the square of the norm of this guy, which is 4 times this guy. Okay, you guys follow. I hope I didn't make any mistake. Hopefully you follow this. So this one will be 0, 1, 1, 1 minus 3 over 4, 1, 1, 1, 1, which is going to be equal to negative 3 over 4, 1 quarter, 1 quarter, 1 quarter. Do you guys follow this? It's pretty straightforward. It's basically just using the formulas. So instead of using this, if you use this, you will have a lot of fractions to deal with. So we will use V2 equal to this guy instead. Okay? You are allowed to scale it without affecting the answer. So we are nearly done. We just need to do one more step. Okay? So the next step here, our final step. U3 is that guy. Minus the projection of U3. Okay? Dot the V1, and then you have to dot the V2. This is dot V1 first. The square of this magnitude, which is 4, times 1, 1, 1, 1. And then subtract. Now this works because V1 and V2 are already orthogonal. Okay? Please subtract this guy. Dot the second one. Minus 3, 1, 1, 1. The magnitude of this one square, 9 plus 10, 11, 12. Is it okay? It's just a bunch of computation now. One half minus 2 over 12. Minus what? Minus negative 1 half, 1, 6, 1, 6, 1, 6. Is it okay? So I end up with this. Okay. So now I now have my answer. Let's check, make sure it's okay. 1 half, 1, 6. Yeah, it seems right. Okay. Yeah. Okay. You guys good? So we now have my orthogonal bases. W is spanned by these three vectors. These are now supposed to be orthogonal. That's my first one. That is my second one. My third one is this guy multiplied by 3. We'll use V3 equal to 0 minus 2, 1, 1. Okay. Can we check whether they are actually orthogonal? Can you mentally check that? I'm pretty sure they are. Yes, they are. Any questions so far? It is just using the procedure I wrote on the board last time. Are we okay? So this is the procedure demonstrated by an example. You can actually scale the stuff. You can get this, once you get this result, you can scale it to make your calculation easier. Okay? So you end up with this. So this one is now a orthogonal basis. What happened if we want a orthonormal basis? What happened if I want an orthonormal basis? Orthonormal basis will be written like this. How do I change it from orthogonal to orthonormal? Unit vectors. So this guy need to be divided by the norm of this, the magnitude of that vector, which is 2. Now this guy has length 1. 1 quarter, 1 quarter, 1 quarter, 1 quarter after you square them and you add them up. What do we need to divide this guy by? 9, 10, 11, 12. Divide by 12. Not 12. Square root of 12. What do I need to divide this guy by? Square root 6. Okay. Do you guys have any questions? If not, I am going to, oh my God, I only have 10 students. I only have 10 students. It's supposed to be a 30 student class or 26 student class. Okay, so don't know where everybody is. Okay, so any question for this? I'm going to go to the next section if you don't have any question. Can I move on?
Yes.
Yeah.
Okay, we will do that. Okay, we'll move on to the next section. The next section is called least square problems. How do I solve something like this? You guys remember how to solve something like this?
Put it in the matrix and do RREF.
Yes, very good. So you just put this together. And do RREF. When we do RREF, we end up with this. What does that mean? Oh, sorry, this is a 0. What does it mean? So what will be the answer? So x will be equal to
1 or
1
no,
and
1, 2.
1, 2. Is B in the column space of A? Is this B in the column space of A?
Yes.
Yes, because it's a linear combination of the columns of A. Because this system is consistent. Answer is yes. It's a similar problem. Okay, it's a similar problem. Then I will do something similar to that. Do RREF. What does that mean? So what's the answer for x? How do we interpret the result?
Is it there isn't one because the bottom row you have 2 zeros and then a 1.
Yeah, so no solution. The system is inconsistent. Is B in the column space of A? Is it yes or no?
No.
The answer is no. Okay. So B is not in the column space of A. Now, this is what we are going to do. We're still focusing on this example, okay? Still focusing on that example. B is not in the column space of A, but we can do the following. So this is the column space of A. Okay, and this is my B. Now B is not there. That means something like that. Okay. I want to find, okay, the goal is to find the vector in the column space of A, okay, which is closest to B. Okay, there are many vectors here in the column space of A. Okay, there are many of them. All these are vectors in the column space of A. But I want to, in particular, find the one that is closest to B. So I'm actually trying to find projection. So this is continuing with this problem. Find projection of B onto column space of A. Okay? How do I do that? Finding the projection, we have some formula. Okay. The formula is that projection of B onto the column space of A. Okay, this is the column space of A. It's going to be B minus some stuff, B dot, let's call this B1 then, over B1 squared times B1 minus B dot B2 square times B2. Okay, and that will be the projection. No, not yet. This is the projection. This is the projection. If I subtract them, it will be the other vector. I'm sorry, we don't have that term, so it's just these two. That will be the projection. Now, but this is under the assumption. This is under the assumption about what? This is under the assumption that these two are actually perpendicular. Okay, these two are actually perpendicular. So I need to somehow find, but are these two perpendicular originally? These two? Are these two perpendicular? I'm going to call this U1 and U2. Are these two perpendicular to each other? That guy with these two spans the column space of A. Are they perpendicular to each other?
No.
Okay, they are not. Okay. So I need to, how do I get something that's perpendicular to each other and also span the column space of A? So I use what I just learned a little while ago, which is the Gram-Schmidt orthogonalization process, Gram-Schmidt process. That process says that V1 is going to be equal to U1. In this case, is 4, 0, 1. Okay, my V2, this is my V2 now. My V2 is going to be equal to my U2, which is 0, 2, 1, minus, okay, minus what? Minus 0, 2, 1, minus 0, 2, 1, dot 4, 0, 1, divided by the square of the norm of this one. I believe it will be 70. Is it okay? Are you guys following me? So this will be my V1 and V2, and they will be orthogonal. And this guy is going to be equal to what? I'm running out of space. What do I do? A is equal to, I'm just putting it into this place too, so that I can use the whiteboard more economically. Okay, so what do I have? 0 to 1 minus 1/17 of 401. Yeah. Okay, 1/17 of 401. Okay, what is this? 0 minus this negative 1/17. 2 minus this is 2. The third one is 1 minus this. 1 minus this is 16/17. So we can use V2 equal to minus 1, 34, 16. I hope this is correct. This is not correct. I messed up somewhere. Can you guys help me? 2 minus 0 is 2. Oh, this is a 4. Okay, it's better now. Okay. Okay. Maybe I can actually, I don't even need this one. I can use one. I can use half of that. Okay, because all these are even numbers. Minus 2, 17, and 8. Okay. So now I have this guy. Okay, let me just summarize it. V1 is 401. V2 is minus 2, 17, and 8. Are these two orthogonal now?
Yes.
They look like it's orthogonal. Okay. Okay. So now the projection, this one that we want. Okay, this one that we want. Projection. Column space. Column space A. It's going to be B, which is 2, 0, 11. Okay. Dot V1 or 0, 1 divided by V1 squared 17 times V1 plus V dot V2 divided by a big number here. What is that? So what do I have here? Do I do this right? Oh, this is 88. I just try to make sure that I do all this correctly. So the number seems to be really big. V2 square. Let me make sure that I have everything correct.
Yeah, 357.
What?
It's
What's that?
357.
I just want to make sure that I have things correct. Minus. So what do I end up with this? Minus 4, 24, 16, negative 2. Okay, so yeah, I'm sorry, I'm getting too bogged down on these details. Is it 357?
Yeah.
Okay, so I just want to make sure I didn't make any mistake earlier. Okay. 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 Did I make any mistakes, guys? I don't get exactly the same number as before. That's a problem. Let me see what my V2 is in my notes. I'm sorry about that.
You want to explain the first step, the projection of column A, or of projection of B onto column A equals B dot B1 over B1 squared?
This step?
Yeah.
The projection? Okay. I can explain this step. Because B is equal to, okay, here's the explanation. Yeah, I'm sorry these numbers turn out to be kind of ugly. I don't know whether it's because I make a mistake or something else. I can explain to that. Let me try to figure this out. It's not supposed to be so complicated. I just want to make sure my V2 and V1s are correct. So I have V1 equal to 401 and V2 I have minus 4 over 17 to 16 over 17. And that's supposed to be correct. Okay, so the reason for this is the following. So B, let me explain that step. Hopefully it's coming back to you, okay? The reason for that is this. B is equal to C1 V1 plus C2 V2. Okay, then you dot both sides. Okay, so B, we used this before. Okay, so this one will be C1. You dot this, then you get this guy. Will be,
what are the V's?
huh? What are the V's?
Yeah.
The V's are the orthogonal vectors. The V's are the orthogonal vectors. Okay. The original vectors, the U's are these two. Those two are the U.
Then how, if the V's are in the plane of column A, how do they get to B?
The original U, these are in the column space of A, right? You have two vectors in the column space of A. Okay. And I want to do the projection. when I do the projection, in order
Oh,
to do
okay.
projection, I have to have V1 and V2, which are orthogonal.
Wait, but you said B equals C1 V1 plus C2 V2.
I want to write this as a, okay, sorry, the projection of it.
Okay, that makes sense.
Okay, so this guy has B is equal to this guy plus C. Okay, and this guy is C. Okay. And then you start to dot this with V1. Okay, then you get this because this one is going to be gone, right? When you dot this with V1, so this V2 dot V1 is gone and C dot V1 is gone.
So is that B or the projection of the B?
This one is B. If I fix it with the C here. B is this guy, the projection. This guy is the projection. Okay.
Okay.
Is it okay? We used the same technique before. That's how we arrive at this similar type of formulas. Okay. So we write B as C1 V1, C2 V2, plus this orthogonal vector. This one is in the curve of, if we call this W, this guy is in W curve. Hopefully this is coming back to you. So from this, I get C1 equal to, C1 will be B dot V1 divided by this. And similarly, you get C2. I mean, it's a technique that we use. Basically, that's why we have that formula for the orthogonal, for the Gram-Smith process. Is it okay? Yeah. So I don't worry about the computation too much, okay? The computation is really ugly, okay? But at the end of the day, all this is going to simplify to, I'm going to skip the computation because it's too ugly. I want to focus more on the conceptual stuff. So it turned out to be 443. Okay, that is the projection. Okay. Eva, did I answer your question here?
Yeah, thanks.
Okay. So the projection is 443. Okay, so I mean, I skipped a bunch of calculation here, but I think everything is correct based on what we did and based on my notes. Okay, and eventually all this will just magically simplify to 443. Those are arithmetic stuff. You don't want to be too bogged down on the arithmetic. Okay. So what we are trying to say is that here we project this B into the column space. So we want to introduce this concept about W. W is a subspace, right? That can, in this case, it's a column space. I'm trying to introduce some conceptual stuff here. Okay. Any questions so far? So this guy turned out to be, after all this computation, is equal to 443. Okay. Do you have any other questions on this process? Okay. So projection of this onto the column space of A is going to be 443. It's going to be 443 in this situation for this particular problem. Do you guys have any questions about the conceptual part? The arithmetic, don't worry about it too much. Okay. So what we did is to use this formula here. It's a projection, which we did like last time, I think. The main thing is that when you use this formula, it depends on the fact that these two are perpendicular to each other. Okay? Those two are perpendicular to each other. So you need to start out with these two columns, which are not, these two columns are not perpendicular to each other. And you have to manufacture two vectors also in the column space of A, which are perpendicular to each other. That's all we are trying to do. So conceptually, this is what's going on. I'm going to erase most of this arithmetic. Okay. So this is what we are saying. So this one is equal to column space of A. Projection of B on the column space of A is equal to 4, 4, 3. That vector 4, 4, 3. Okay. After we did a lot of stuff. Okay. So part C. Find the distance from B to the column space of A. So what would that be? The distance of this vector to this W, which is the column space of A, is going to be the length of some vector there.
Z.
The length of
Z.
which one? Z, right? The length of this vector. Is it okay? It's the length of this vector. Okay. So this is going to be equal to, so the distance is equal to the magnitude of C, which is turned out to be 4 squared. No, not 4 squared. You need to do the subtraction first. Okay. It's the distance of B, which is the original one, minus the projection. Minus the projection. Okay, which is going to be B is what? 2011 minus 443. What is it equal to? Minus 2, minus 4, and 8. And I want the norm of this, which is square root of 2 squared plus 4 squared plus 8 squared. Square root 84. Is it okay? Do we have any questions so far? So this is going to eventually lead to some important concepts here, which is going to have good applications, but we are just building it up. Are we okay up till here? Okay, next. Okay. Part B. So AX equal to B hat, where B hat is the projection. B into the column space of A, which is equal to 443. Okay. Do you think this will be consistent now? We want to solve AX equal to 443. Do you think it's going to be a consistent? This is my A. Okay. So you will do 4, 0, 1, 0, 2, 1, 4, 4, 3. And we do RRVF. Do you expect this to be consistent? We actually do, because this 443 is in the column space of A. 443 is in the column space of A. It's equal to this guy. Okay? It's a linear combination of V1 and V2. The span of V1 and V2 is the column space of A. So we expect this to be consistent. And when we do that, we actually end up with, was it the first problem we did? Did we do this problem before when this is 443? You guys remember?
Yeah, we got x equals 1, 2.
Okay, so it's going to look like this. So x is equal to 1, 2. Okay. So let me try to recap a little bit here. Okay. I'm going to erase most of this and save the picture. Okay. This is a recap of what has happened. Okay. This is my original B. Okay. This is my original B, 2, 0, 11. This is not in the column space of A. Okay. That's not in the column space of A. So when you try to solve it, it's inconsistent. Okay. When you try to solve AX equal to B, you get inconsistent. But when you try to project this guy onto the column space, okay, project this onto the column space, okay, so you get this guy B hat, which is equal to 443, which is the projection of B onto the column space of A. Because you project onto the column space of A, by definition, this guy is in the column space of A. And this guy is in the column space of A. So when you try to solve this, by definition, this guy is going to be consistent. So this one is consistent. And it turned out that that answer is x equal to 1, 2. Okay? That guy is consistent. So what we have done is that we have found, okay, we have found x this guy here, okay, B hat is the vector in column space of A closest to B, which makes AX equal to B hat consistent, which means it makes the system consistent. Which means AX consistent. So among every single vectors, okay, in the column space of A, there are many vectors in the column space of A. Of course, each of those vectors will make AX equal to that vector consistent because that's the definition of column space. The one that has the closest to this original vector B is the B hat, which is the projection. Okay. Any questions so far? Another way to say this, okay? Another way to say this is the following. this guy here. Let me do it slowly to make sure everything is good. Okay. How are we doing up till here? Okay. So I want you to understand this. Now this is the original vector B. Okay, this is the original vector B. Now I end up with this guy 1, 2. Okay. Now A times 1, 2. A times 1, 2. Now A times 1, 2 is actually A times 1, 2 is actually 4, 4, 3. Okay. B minus 4, 4, 3. So this distance here, the one we got, whatever that number is, square root 84. Okay, that we got. That was the square root 84. Was it square root 84? Square root 84. That number we got square root 84. So this number here is square root 84. Okay. It's the one which is more shortest distance to B. So any x, for any x here, this guy fall into the column space of A. So the distance from B, the distance from this vector to any vector in the column space of A times x is some vector in the column space of A. So B minus this vector in the column space of A, that distance will be bigger than this distance, will be bigger than square root 84. This is just saying that this one is the shortest distance. Any questions so far on this?
Why do we want to know the shortest distance?
Pardon me?
Why do we
want
the
to know the
shortest
distance? It's coming up soon. It's coming up soon in some application in the next section. Okay. So have you done regression analysis, fitting a bunch of points using a straight line?
like that least squares that?
Yeah, the least square. Yeah, the next section is called least square approximation.
Oh.
This is least square problem. The next section will be least square approximation. So all those stuff that you do in Excel, where you fit a bunch of points using a straight line, can be done using either calculus or linear algebra. The way to using linear algebra is actually much faster and cleaner and nicer. Calculus, you can do this. You just take a lot of partial derivatives. Okay.
That's
so
cool.
Okay. So once we get through this, we can get to the next. Once we get to the next section, you will see. Okay, you will see. So we actually can formulate that problem, that least square approximation problem, in terms of this. And then you will be able to see how that is applied. All this is trying to lead up to that least square approximation stuff. Hopefully this helps. I apologize, some of these earlier numbers are so ugly. Okay, so let's just write this formal definition here. Okay, We'll write this formal definition here. And then we will very soon be able to do this application. Application is going to be on Monday, I think. Okay? It's on the next section, which is Monday. Okay. The earlier example we have, is, I believe this B here is 2011, if I remember correctly. And this X hat here is my 1, 2. Okay. And AX hat here, this guy here is my 4, 4, 3. Okay. Takes a look like this. This is column space of A. This is vector B. And this is perpendicular. And this guy here, this vector here, is my A X. Okay. So that X hat, okay, is called the least square solution. Okay. Least square solution means that the AX hat is the vector in the column space so that this distance is the smallest. This distance eventually will represent your error in your approximation, in your regression analysis. Okay. So I'm going to derive another way of finding what this X hat is. Okay. The earlier way that we did was really long. Okay. We need to do orthogonalization process and all this stuff. That one was very long. So here we are going to be deriving another way to do this to make this a lot shorter. Okay. So we are going to watch this. So I know that AX hat is equal to B. Okay. Which is the projection? Equal to B hat. Which is, and this B hat is the projection of B into column space of A. All right. What does it mean? Okay. That means B minus this guy, AX, and this guy Now this guy is going to be this vector. So this guy is going to be this vector C. Okay, this vector C here. This is the vector C. Okay, this is the same as the vector C. Okay, this one is going to be in. This one is perpendicular to the column space of A. Okay, do you guys agree with that? So this difference is this vector, which is essentially the error vector. Okay, so this guy is perpendicular to W perp, and W is this guy, so it's perpendicular to column space of A. What does that mean? That means if my A is written as A1, A2, and so on, it's a n by n matrix. An. Okay, that means this guy here dot each one of this, okay, is equal to 0. Is it okay? This dot product is equal to 0 because this one is perpendicular to the column space of A. And then AI span column space of A. Hopefully you still follow. What does that mean? This means that now this is dot product, this is a dot product. I can rewrite the dot product. So these two vectors look like this guy dot this guy. Okay. I can rewrite it so that this guy is a matrix product. Okay. By instead of taking this AI, I think of the AI transpose. This one will be AI, and this one will be AI transpose. Okay. So I'm going to think about this transpose here. Okay. So instead of a column, this will become a row. Okay. So next, okay, what we are going to do is to write it like this. But this is true for all I, for all the columns. So I can write it like this, A1 transpose, A2 transpose, all the way up to down to AN transpose. Okay, so this guy, this is no dot here. This is a matrix multiplication here. This is a matrix multiplication. I'm writing all this matrix multiplication, all n of them, in one shot, look like this. Okay. Now, this is just A transpose. That guy is just A transpose. Because I'm just basically changing all the columns to rows. So now I actually have the following. What I have is that A transpose, this whole thing is A transpose, B minus A x at is equal to 0. Okay? Okay. I am going to do this here. Look at this equation. AT B minus AX at is equal to 0 vector. Multiplying this out, you will get ATAX equal to 0, which means that ATAX is equal to HTB. And this is called the normal equation. And this will provide you a very fast way to find your projection. Okay, because this guy is the projection. AX hat is the projection. If you do it this way, it's a lot faster and you don't have to do this Gram-Smith process. Okay, so we are doing this same problem that we have earlier with this approach. Okay, the same problem. Exactly the same problem. Okay, of course we expect to get the same answer. Okay, we expect to get the same answer. The answer should be 1, 2. Okay, so what do? We take the original problem, take this original problem, multiply both sides, multiply by A transpose. Then you have A transpose A x equal to A transpose B. And then you solve. Okay. So what do we have? So we basically have to solve this system. This is A. This will be A transpose. Okay. We're solving this system. This one I'm going to call X hat here. Okay. Times X hat equal to A transpose, which is 401, 021 times B. So what do I have here? What is the size of this matrix after I do this? 2 by 3 and then 3 by 2.
2 by 2.
2 by 2, 17, 1, 1, 17. Now this matrix is always symmetric. It's always a symmetric matrix. Did I tell you what a symmetric matrix is before? After you transpose it, it's the same as itself. Look at the rows and the columns, they're the same thing. Because if I transpose this guy, I will end up getting itself. Quick digression. AB transpose equal to B transpose A transpose. So A transpose is this second one transpose, and then the first one transpose, but the transpose of the transpose is itself. Okay, so I show that the transpose of this guy is itself. So it's symmetric. It's always symmetric. What is the other side? 401, 8, 19. Is this 19? 8 plus 11. And the other one is 11. 19, 11. You solve for this. You solve for this 17, 1, 117. Yeah. You will get this. You will get your 1, 2. Okay? Or you can also use the AD minus BC and all this stuff too. It doesn't matter. But the idea is that you will get your X hat. So this guy is going to be, this answer turn out to be 1, 2. If you want the projection, it will be A times X hat. Okay, so A times X hat So a times x hat, which is this guy, times 1, 2, is going to give you the 4, 4, 3. So the least square solution is really just straightforward then, okay? You just take your original equation, multiply by A transpose on both sides and then solve. That will be the least square solution. And you multiply that back by A will give you the projection. I think we finished this section. We are going to just that put us in a position to do a bunch of application next week. Next week, we will talk about how we use this to solve a bunch of problems. It's not a bunch of problems in regression. The one that you are most familiar with is probably this. You have x and y. You're given a bunch of points. Okay. You are trying to fit the best line through this. Okay. We are going to look at this problem as a problem with column space and linear algebra and all this stuff. Okay. And all these errors, the square of these errors, okay, the square of those errors is going to be equal to the square of the error, the square of that magnitude of that z vector, which is in the subspace perpendicular to column space of A. So we will talk about that next week. It will be kind of interesting to see how this is all applied. But that is why we are doing this. Thanks for coming to class. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people. Out of 26.
Professor, I have a question.
Yes.
I know finals don't start till, I believe, 2 weeks from now. But when will you have the study guide for the last sections available?
For the final exam.
Yes.
I will try to do my best. I will try to work on it this weekend, but I'm not sure.
Okay.
Whether it will be available yet. It's just because it takes a long time to make the exam now. Because I have to try to make it a little bit. I have to spend more time on making the exam. To make
okay.
It. Yeah. So I'll try to do it this weekend. Yeah.
All right.
I have the differential equation one available, but not discussed yet. So I'll try to work on it.
All right. Thank you, Professor.
No problem. Yeah. But the final exam is coming up in a couple of weeks, 2 weeks or something.
Yeah, it's coming up quickly.
It'll be over 2 weeks. Over 2 weeks. After this week, we have 4 more classes. We have four more classes for this class for linear algebra, and then we'll have the final. Yeah.
All right. Thank you. Thank you.
Okay. See you guys.
Bye, Professor.
Professor,
Bye.
looking forward to next week.
Thank you. Bye bye.